All right, so we've talked about the various shapes and angles of our molecules. So again, this is going to stem from your Lewis structures. You got to draw your structure correctly first, then you can analyze how many sets of electrons, get the angles, get the shapes, electron geometry, that sort of thing. The next thing we want to think about that stems from all this is the polarity. So I just went back to my initial page here. And this is kind of a mental imagining of what is happening with the electrons. So I think the best way to think about this is just from the perspective of developing a structure. So let me give you a couple definitions here first, and then we can kind of do some examples. So basically what we're looking for is either molecules are either polar or they're non-polar. And when we use this term polar, we're describing the electron distribution. So a polar molecule, we could say, has uneven electron distribution. And if the electron distribution is uneven, that means the molecule would have a negative side where there's more electron density and a positive side where there's less electron density, right? And those would be kind of like the poles, the positive pole and the negative pole. So there'll be a negative side or negative end of the molecule and a positive end. And that's one of the reasons why we want to know about this. Having a negative end and a positive end will change the physical properties of a certain type of molecule. So one of the first things we'll talk about in Chem 2, if you go on to take Chem 2, is how a molecule being polar changes what we would expect about maybe its physical properties, like its boiling point, compared to one that's nonpolar. Molecule is nonpolar, it has an even electron distribution, meaning the electrons are distributed evenly around the molecule. And if that's the case, there's no negative end and positive end. So there's just no charge distribution. The electrons are everywhere evenly. Okay. Now we need to figure this out, right? So how will we approach figuring this out? What we really want to initially think about is the bonds. So we're going to start by thinking about bond polarity. And bond polarity is just a function of electronegativity. So if we look at a bond and we look at the electronegativity values of the atoms involved, we can identify whether those electrons are evenly shared between the bonded atoms or whether they are unevenly shared. So just as an example, right, if we have a bond between the same two atoms, like two nitrogens, both nitrogens have the same electronegativity. So there's no difference in electronegativity between the atoms. So there is no unevenness about the electrons. They're not pulled to one side or another. So this would be a non-polar bond. Right? This is different if we have two atoms in a bond that do not have the same electronegativity. So imagine we have something like an oxygen-hydrogen bond. Right? So you can look at position, recognize, oh, oxygen's a lot further to the right, it's going to be more electronegative, right? But we can also get the values from the periodic table, right? The one we're using for class has those values. Oxygen is 3.5, hydrogen is 2.1. That means this would be a polar bond. That means the electrons are not evenly distributed. They are going to be pulled more towards the atom with higher electronegativity. So the way we can indicate that is with what's called a polarity arrow. So it's an arrow, but at the tail is a sort of a plus sign. It's sort of incorporated into the tail. Right? So that plus sign would be on the side of the bond where the less electronegative element is, and the point would be on the side where the more electronegative element is. And that indicates the draw of the electrons. The electrons are being pulled more towards the oxygen than they are toward the hydrogen. Now, we could do this for any bond that shows up in any molecule we have drawn and decide, is the electronegativity the same? Is it different? Right? And you may even be able to go into grades of how different it is. If it's really close, that'll be a slightly polar bond. And if it's really different, that will be a much more polar bond. Right? In fact, there's a threshold where you might decide this is less of a shared bond than it is a transferred bond, right? So we've kind of talked about broad categories of ionic bonding versus covalent bonding, right? There's really a continuum from the electrons are completely shared to there's a real uneven sharing, right, that would eventually result in what we would classify as an ionic compound, where the metal lost the electrons, the non-metal gained them, right? You could think of that as just a very, very polar bond with a big electronegativity difference. Okay, so if we go through a molecule and we identify which bonds are polar and which aren't, and particularly if you're thinking about this arrow, I think is helpful. The way we determine if the molecule is polar, so let me call that molecular polarity. The way we do that, polarity, I missed an I there, is by adding the bonds together. Add bond polarities. Okay, and that is, if we have a reasonable understanding of our structures at least, that shouldn't be too hard to do. Now, let's do some examples, and let's start with this simpler system. So let's look at some polar molecules, some molecules with two sets of electrons around the central atom, and let's evaluate whether they would be polar or nonpolar. So carbon dioxide is one of our favorites here. That would be a linear molecule, 180-degree bond angles, right? And we would want to think about whether or not that is polar. Now, for comparison purposes, let's look at something like carbon with a sulfur on one side and an oxygen on the other side, right? Similar structure, but some differences now. So if we look at the first one here, carbon dioxide, we can look up the electronegativity differences between carbon and oxygen. So carbon's 2.5 and oxygen's are 3.5. So yeah, that's a reasonably big difference. These are polar bonds. But the important thing here is we want to think about how the bonds relate to the other bonds in a molecule. This carbon-oxygen bond is pulling electrons to the right-hand side, but the other carbon-oxygen bond is pulling electrons to the left-hand side, right? So it's almost like a tug-of-war. One oxygen is pulling one way, the other oxygen is pulling the other way, but the oxygens have the exact same strength. So they don't pull the carbon in either direction in that kind of imagined analogy. Well, if the strength, even if the bonds are polar, if they're pointed in direct opposite directions like they are here, if we go to add those two arrows together, they're going to cancel out. And when the arrows cancel out, there's not an uneven distribution. That is a non-polar molecule. Now, what we see here is the arrows would not cancel out. We said oxygen is 3.5, carbon is 2.5. Sulfur, and again, you can do this by position, but if we have the values, that will eliminate any uncertainty about different columns or different rows, maybe along a diagonal or something like that. Carbon and sulfur have the same value for electronegativity, so that is a non-polar bond by the electronegativities involved. So there's no arrow for that bond, but there is a polarity to the carbon-oxygen bond. So in this case, right, if you imagine this as a tug of war, right, one side gets ready to pull, the other side isn't even pulling, right? They all let go of the rope maybe. And that means one team pulls all the electron density this way, right? Now, the electron density isn't going to be pulled away from where the molecule is, but it's going to be pulled to one side of the molecule. So this molecule would have a negative end on the left side, and if the electrons were pulled away from the right side, it'll be positive on the right. Now, one way we can indicate that is with that symbol, which is the lowercase Greek delta, and in this case, it's indicating partial. So it would be partially negative on the left side, and the molecule would be partially positive on the right side. There are the two poles we talked about when we described molecules being polar. Negative pole, positive pole. This is a polar molecule. Okay. Now, that is essentially what we want to do for every example of geometry that pops up, is we just want to evaluate the electronegativity of all the pieces. So I think once you have a good handle on your shapes, this should be fairly easy to apply. But always remember you can find your electronegativities in your periodic table if you need to. But I think there's an important general idea that I want to describe in a little more detail as you're doing this, and that is symmetry. So for symmetrical molecules, right, it is going to be very likely that they are going to be nonpolar. And let me give you a real quick example. Let's jump up to 4 and let's jump up to tetrahedral structures. Right? Imagine that I put a carbon in the middle and I attach hydrogens to it in a tetrahedral arrangement. Right? Now, electronegativity wise, carbon's actually a little more electronegative than hydrogen. So all these bonds would actually be pulled a little bit in toward the carbon. But this is a symmetrical molecule. There are 4 bonds. They're evenly spaced around the carbon. All of these pulls are canceling each other out. This bond, the electrons are being pulled down, right? But for all of these bonds, there's a little bit of that arrow that is pulling the electrons up, at least in the way I drew that structure. So this molecule ends up being nonpolar. Right? Because even though there's a difference in the bonds, it's a symmetrical molecule. Right? The same is true here, even if there's a very big difference in the other direction. If I put 4 fluorines in here, fluorine is much more electronegative than carbon. And that means all of these bonds are pulling electrons away from the carbon. So these bonds would all be pulling out. But again, if it's a symmetrical molecule and all of the bonds are being pulled out, they're all canceling each other out. This one is pulling up, but all of these have a component that is pulling down, right? Even though they're not directly pointed down, they're all pointed to some extent down. This molecule would also be nonpolar, right? And it's symmetrical, right? But what happens if we break the symmetry of the molecule? What happens if you have just 1 fluorine? And say the other 3 are hydrogens, right? And this would be the same thing if you had 2 hydrogens and 2 fluorines, or you had 3 fluorines and 1 hydrogen. We break the symmetry of the molecule, the dipoles of the bonds will no longer cancel out. The fluorine is pulling away from the carbon, but the carbon is a little bit pulling away from all the hydrogens. There's no canceling now. The electrons are pulled up toward the fluorine. We'd have a negative side of the molecule and a positive side of the molecule. This molecule would be polar, right? We break symmetry when we have non-bonding electrons as well. If you think about a similar molecule here, like ammonia, right? It's a trigonal pyramid. And because one of the positions there is a lone pair, there's no dipole. There's no bond dipole for a lone pair. Lone pairs are just there. They can't pull electrons to one side or another. They do affect geometry, and you have to factor that in. But in this case, there's no way to cancel out any of these arrows because we just don't have the 4th bond to involve what is happening there to cancel out the pull or push based on these other bonds. So this type of molecule, where it's not that most symmetric version, like a tetrahedral, will always be polar. Right? The only possible way for it to be polar is if all the atoms have the same electronegativity, right? And that makes it really unlikely that one's in the middle and the others are all around the edges of the molecule. So your trigonal pyramids, your bents, your angulars, they are always going to be polar. Okay. All right, so I think that's a good description of polarity. Again, practice that as you're doing your Lewis structures and as you're practicing your shapes and angles.